Welcome to my talk, Cloaked and Pixels, Concealing Payloads with Steganography. Before I get into it, I just want to say thank you for everyone coming to this talk. Let's get on with it. Quick agenda. I'm going to start off with an obligatory who am I, introduction to myself. I'm then going to move on to an introduction to what steganography actually is, what is this talk all about, and I'm going to mention a few cases in history where steganography is being used to achieve some objective. And then I'm going to get to the heart of the talk, which is a proof of concept shellcode encoder and runner I wrote a little time ago. I'm going to explain the code and do a semi-live demonstration. And then I'm going to switch seats, move to the blue team side, and do an analysis of a few samples of malware that abuse steganography for evasion. So, who am I? I'm Ben. I go by the online handle Polygon Ben. I've got links to 2 blogs there and a YouTube channel. I upload CTF walkthrough, hackbox sort of things, and malware analysis occasionally. In my full-time job, I'm a senior analyst at Accenture in the SOC, and I got into security around when I was 14 or 15. There was a government-funded scheme called Cyber Discovery. There's me there at one of their sort of in real-life CTF events. What is steganography? The word itself originates from the Greek words steganos and graphia, and that roughly translates to covered writing. So that gives us sort of an idea what it really is. If you look at the official definition, steganography is the practice or the art of concealing information within another message or another physical object or another medium with the aim of avoiding detection. So let's have a look at a few cases in history. The first ever recorded use of steganography was approximately 500 BC. There was a Greek ruler called Histiaeus, which I've probably messed up the pronunciation. He was the ruler of a city called Miletus, and he was being held captive against his... he was held captive by King Darius in a Persian court, and he wanted to send a message to his son-in-law, Aristocras, to tell him to start a revolt and start a revolution. But he couldn't afford for this message to his son-in-law to be intercepted and to be read and the plan to fail. So he got his most trustworthy slave, shaved his head, and tattooed the slave's head and let it grow back, and then sent the slave on his way to deliver the message to start the revolt. If we go forward roughly 2,500 years, we get to around Nazi Germany time, and German spies were using microdots to smuggle photographs or documents on benign objects. A microdot is a downsized photograph. It is incredibly small, literally the size of a dot. It can be as small as 1 millimeter in diameter, and they had a fancy contraption of lenses, and it downsized a regular document onto, let's say, a doll or a benign object, a letter, and it was used for espionage to carry documents across borders in an attempt to stop evasion, in an attempt to stop it being found or detected. So we've got 2 cases so far. One involves steganography to send a secret message, and the other is used for espionage. The remainder of this talk, we're going to be talking about digital steganography. This is a subset of steganography which really only involves embedding data or a secret message or whatever within a file. And the context we're talking about digital steganography is malware or malicious code being embedded within an image as an attempt to evade detection by antivirus. So that's what digital steganography is. If you're creative enough, you could use any particular file type for steganography. However, in the wild, we see certain file types are more prevalent than others, like PNG, JPEGs. I haven't included it there, but SVJs are quite prevalent, as well as your regular Word docs, Office stuff. We see that quite a lot. So I'm going to be talking about a subset of digital steganography, and this is least significant bit steganography. And LSB steganography abuses the fact if you've got an image and the image is made up of pixels, and each pixel has a number or multiple numbers representing the strength of the RGB components. If you modify the least significant bit of each of those, each binary representation of the RGB components of a pixel, it doesn't impact the image, it doesn't impact the color massively, and you can encode data in that. If that didn't make much sense, it doesn't matter. I'm going to explain this in a lot further detail because it's important to understand. So, we can take a step back. I'm going to ask the question, how are digital images stored? And I'm going to generalize here, and I'm going to say they're made from an array of pixels. This begs the question, what is a pixel? How do you define a pixel? And a pixel is the smallest unit of a digital image that can be individually controlled or manipulated. And when I say individually controlled and manipulated, I mean, can we change the color of it? And yeah, they are literally the building blocks of an image. If you have a high resolution image, it's going to have tens, maybe hundreds of thousands of pixels, and each of those pixels represent a singular point with a singular piece of, with a singular color. So, I mentioned it again. Pixels contain color information represented by a combination of values for red, green, and blue. This is quite an important point. There's a good analogy of this sort of pixels and RGB, and I'm going to show it here. You can see there we've got extracathedral. It's a bit dark, but you can see it is extracathedral. We see this is open in an Excel spreadsheet. So what I'm going to do is I'm going to play this. And we can zoom into this Excel spreadsheet, and I do so, and we can see this is not an image, it literally is an Excel spreadsheet. Let me just pause that. And what we've got there is a pixel. This highlighted box you can basically think as being one pixel. And the pixel contains a number which represents the strength, or it contains three numbers which represent the strength of the red, green, and blue components. So I've got another photo there. Each of these pink boxes is a pixel, and each pixel contains three numbers to represent the strength of the RGB components. The strength can go from 0, which is the weakest, to 255, which is the strongest strength. So, by the way, that photo to spreadsheet thing I showed you, you can try it out yourself on this link here. You just upload a photo and it spits out the spreadsheet instantly. So, to understand least significant bit steganography, a very basic bit of binary knowledge of binary is necessary. Very, very basic. What I've got here is a little web page I wrote where it automatically converts from binary to decimal back and forth, and it sort of shows you how it translates here. So we've got the decimal, and decimal is what we count in. This is base 10. There is 10 symbols, 0, 1, 2, 3, up to 9. Binary is just another way to count, but you only got two symbols available, 0 and 1. We can see at the moment we've got the decimal number 157, and then we've got the binary conversion of that, which is 100, 111, 01. Down here we've got powers of 2, starting at 2 to 7 and decreasing. If we start at the top here, we can see we've got a 1, and that indicates we want to include this 2 to the 7th power, and then 2 zeros, because we don't want to include the 2 to the 6th and 2 to the 5th power, and so on and so forth. What we could do is just play around with this and modify it, and what I'm going to show you now is we can maybe change this 1 on the end to a 0, and we can see it's 157, and it now goes to 156. And we can play around, we can move it up and down, set it to 0, it's all going to be zeros, or we can set it to the max, and once it gets to there. So at the max we've got 8 consecutive ones, 8 bits, and it comes to 255. If we change the last most right-hand side bit to 0, this would go down by 1. So changing the most right-hand side bit, and it's called the least significant bit, is going to have a small impact on the overall number. In this case, if we change that to a 0, it would be 254. So it doesn't make a big impact on the overall number. Pixels. I said it again, and I'm going to repeat it probably more times. The color of a pixel can be stored as 3 numbers. Each number represents the strength of the corresponding red, green, and blue components, and the numbers are stored in binary, because computers understand binary, from the sort of minimum of 8 consecutive zeros to the maximum of all ones, which translates to 255. So what we can do is we can got another web page here which sort of demonstrates how this RGB thing works. What I've got here is basically an analogy of a pixel, and then I've got the various components for RGB there. What we can do is we can play around with this, and let's say I want to change the red to 0, and it goes to black. All our numbers are we can change that to green, it's only green, and we can change this blue to max, and it's going to be only blue. What we could do is we could potentially mix some of the numbers about and see if we get a different colour. And we can see after doing this, we've got a pink colour. So what I'm going to do now is change all of these least significant bits for the various RGB components. And I want you to notice what impact this makes to the pixel, the colour of the pixel. So that was originally a 1, and it's now been changed to a 0. And if I play this, we're going to change the remainder. We can see we changed the green one, and we changed the blue one to a 0, and it doesn't make a major impact on the colour. And this is important to understand. And once again here, we've got 2 almost identical looking pixels, and we've got the sort of the breakdown of the RGB components there. All we've done is change the least significant bit on each of the RGB components, and it doesn't impact the colour. So if we've got an image which has a very large number of pixels, and then with each pixel, we can modify the least significant bit of the RG or B component, it doesn't impact the colour of the pixel, and by extension, it doesn't impact the colour of the overall image. So what can we do with this? We've got these bits here we can change, these least significant bits, which we can change without impacting the colour, the image, massively. We can encode our data. If you wanted to send a secret message, we can encode it in binary using these least significant bits. So least significant bit steganography encodes the secret message or your malicious code or whatever you're encoding within the least significant bit of each of the RGB components of the pixel. And you can see here we've got a pixel here, the RGB components, and then the least significant bit on the right-hand side. You'll notice you've got an image, it's got a finite number of pixels, and each pixel can store 3 bits of data, so you can, there's an upper limit to how much data you can encode, and that is 3xy, because there's a total of xy pixels, and you can get 3 bits per pixel, so 3 xy bits per image, where x is the width and y is the height in pixels. So we get into the heart of the talk now. I wrote a proof of concept steganographic shellcode encoder and runner in Python. This used least significant bit steganography to encode the sort of second stage payload, which I'll get onto. I'm going to explain the code here. I'm not going to do it in a massive detail, and I'm going to rush it. So I've got 2 previous blog posts linked there. They go in quite a lot of detail explaining this, and I've also got the source code there for anyone who wants to sort of play around with it on their own. I mentioned here, this is just a proof of concept. This wouldn't be suitable for sort of a penetration test or a red team operation. And I'm a blue teamer, so don't judge my code. So there's 2 scripts, encoder.py and shellcode-runner.py. The encoder script, its job is to encode this second stage payload, along with all the things necessary to run this shellcode into an image. That's this script's job. This wouldn't be ran on your sort of compromised host, your target host. This would be ran on your attacking machine, your Kali machine. You'd want to sort of stage this image, prepare the image for execution on your target host. So let's break it down. Here is the full script here. First 4 lines, or ignoring the imports, these lines here basically set it up so we can use it as a command line tool. I've then got this runner string here, and we import the ctypes module, and we use quite a few different Win32 APIs. This bit of code is, so it's a string, and inside the string is further Python code. This string is going to be encoded within the image alongside the shellcode. This will be basically our second stage payload that is executed on your target host, on your compromised host. These lines down here, we then read in the shellcode from an external text file, and then we combine the shellcode and the shellcode is generated in MS Venom with these lines here, and then we basically encode that and encode it within the image. We've got these functions encode LSB and text to binary. I'm going to go over these because they're quite important. This is basically how we actually encode using least significant bit, how we do it in Python. So the function takes three parameters as input: image path, plain text data, and output path. Image path is the file path to the image you would like to encode. Plain text data is your secret message, your second stage payload, which you would like to encode within the image. And the output path is the file path which you would like the image to be written to once it has been encoded. We start off by using this image.open, and this is from the Python imaging library here. This allows us to basically surgically manipulate an image pixel by pixel. So we open the image, we convert it into RGB mode. This allows us to access those RGB components. We then do some calculations to get the maximum data length, and then we call this function here text to binary. It takes plain text data, which is your secret message, as input, and it is just plain text data, and it converts it to a binary string. I'm going to quickly step through this. It's a very basic, simple function. It takes text data as input. It then iterates through each character in this string and stores it under the variable char. It then takes the ORD function of that to get the Unicode integer value for that particular character, and then it uses format to convert the Unicode number to binary, an 8-bit binary number. We then join all those 8-bit binary strings together. So we got to this point here. We then append a string of 8 zeros. What this does, it acts as the end of the data. So when we want to read this on our other script, when we want to execute it, we want to know where does this the data go up to. And we'll add a null character on the end so we can search for that when we're extracting and decoding it on the other script. We then take a copy of the image and store it under the variable encoded image. This is the variable, or this is the image which is going to be modified, and the secret message is going to be encoded within it. We then get to the where we actually do the least significant bit steganography, and I've basically got a triple nested loop. So I first of all loop through all combinations of x, y, so all combinations of pixels, and then I use the image.getPixel function to retrieve those numbers for the RGB components. We then loop through each of the RGB channels to modify, we modify the least significant bit, and we modify it to be whatever our secret message is, and we've got this binary index. This basically tells us each time we encode a bit, it counts up, and there's a check to see if we've basically encoded all the data. If we have, the for loop will stop. If we haven't, it will update the least significant bit to what it should be. We then use the .putPixel function to update this on our new image, and then we save this. So that was the script which takes your secret message, your second stage payload, and it encodes it within the image. This script is the one which does the opposite. It decodes it and then executes it. This one would only be run on your compromised host. Obviously, if you're doing a penetration test or whatever, or a red team operation, you wouldn't call your script shellcode runner. I don't know what you would call it, but this one's a lot shorter, and it's got worse variable and function naming conventions. So we've got this function here, B2T. We had text to binary before. This one's binary to text. And then I've got this decode function, which decodes it, and then pulls out the plain text data, and then I've got some lines at the end here which basically run the code and execute the second stage payload. So let's quickly go through this. We've got this decode function. It takes encoded image path, which is the file path of your encoded image, as input, and then we open it. We convert it to RGB mode once again to extract those RGB component numbers. We then do some calculations to pull out the width and height. We then did what we did before, and we looped through all pixels, and then for each pixel we loop through the RGB components, and what we're doing here is just pulling out that least significant bit. And then I mentioned there was that null byte, the string of 8 bits, which indicate the end of our encoded data. So we find that location, we cut off all the data after that, so we've only got our encoded data, and then we call the B2T, because at the moment it's a binary string, we convert it to a plain text string, and we've got it. So you can see this decode function is called down here, and it's calling it for encoded image path, which is set here to be pop example.png. This string to ex variable, once executed, it contains our second stage payload. And let's quickly go through this. So we decode it. String to ex contains our second stage Python payload, which contains shellcode, which is going to be executed. These lines here, these 4 lines, basically just call the exec function. However, I did originally just call the exec function with this as input, and when I did that and I uploaded it to VirusTotal, it got a load of hits. So I did some very, very basic, trivial obfuscations, split up the exec into ex and ec, and then proxied it through compile and eval. By the way, exec is a function which allows you to execute Python code in a string. So if you've got Python in a string, and if you pass it into exec, the Python code will execute. So we got up to this point, we've got this string to ex variable, and when we run this program, it will pull out the second stage payload from the image, and it will run it. And let's have a look at what that second stage payload is, and sort of break it down. So this is what the variable would contain upon execution. This is the second stage payload, which is encoded within the image. This would flag as malicious. If you save this in a text file or a Python file, whatever, .py, and put it on your disk, Defender would kill it. And using Steganography, we can take advantage of the fact that Defender is not going to be able to decode the payload from an image, and it just wouldn't do that. Antiviruses aren't that good. It doesn't get detected because it's not on disk, and only when it's executed, it is loaded into memory. So, yeah, it bypasses Defender. We've got these first lines here, the buff variable is created, and then we add a load of hexadecimal characters. This is shellcode generated by MS Venom. This is machine code, which is just going to be loaded straight into memory. It can't be read. And the next lines down set this up. We import the C-types library. This allows us to interface with the C data types, and most importantly, the Win32 API functions. So we can see there we're using the virtual alloc Win32 API function. This allows you to allocate an area of memory, and you can choose the permission level. So we can see we've set the area of memory to be the length of the shellcode, which we want to execute, and this OX40 here sets the permission to read, write, execute. If this happened sort of in the wild, a good EDR probably would flag this and at least lead to a detection. Buffer. We basically take the shellcode byte array and put it into the right format to be loaded into memory, and these functions, RTL move, memory, create thread, and wait for single object, they basically just move the buffer into our allocated memory space, move the shellcode into our allocated memory space, and execute it. I've got a live demonstration here. So I first of all, I'm going to show that Windows Defender is enabled, and I'm going to show the process is running. And like I said, this is able to bypass Windows Defender for a basic reverse shell. However, it would likely get killed by any good EDR. So, yeah. The MSMP-ENG process is running, the sort of Windows Defender agent process is running, and I've got 2 machines here. One of them is my Kali machine, my Kali box, my attacking machine, and my Windows machine here is my Windows machine. And I've got the 2 scripts here, v2 encoder and runner. And then I've got an image bsidesexter.png. So let's take a look at the image. And this hasn't been Steganographically encoded yet. It's just a banner for bsidesexter. It looks legitimate. It is legitimate. So we've got that. And then what I'm going to do is I'm going to generate the shellcode. I'm going to show how it's done. And then I'm going to encode that PNG with the malicious shellcode, and then I'm going to do a live demo of it running. So on my Kali machine, I'm getting the IP address of the local IP address of the box using the IPA command. And now I've got this IP address here, 192.168.0.116. I'm going to use MS Venom. It's a penetration testing tool which allows you to generate shellcode, do fancy stuff. In this case, I'm just setting up a basic reverse shell, and then I'm filling out the L host to be the IP address of this box, and the port I want to listen on is 31337. This generates the shellcode there, and we can just copy that. And we're going to move that over to the Windows host, and we're going to generate this malicious image. So I will save this shellcode in text file shellcode.txt. And we can move over to this side where we're going to actually create the image, stage this this malicious image. We can see the command line arguments required, TAC-S for shellcode and TAC-I for image. You supply those, and we supply the image bsidesx.png, and it will encode and save to poc_bsidesx.png. Let's open up these two images. We'll compare the two. We can see if there's any major differences, whether you'd be able to notice it yourself. And then once I eventually get it up. And we've got the two images there, and you can't tell the difference. The one on the right is the one which contains the malicious code, and the one on the left is the normal one. What I'm now going to do is show you how we can actually use this sort of script to execute it and get this reverse shell going without getting killed by Defender. So on my I'm just looking at the script and I'm confirming I've put the right file name for the image, the sort of malicious encoded image there, POC bsidesx. That is all good. So now I'm going to get a listener on my Kali machine. So what a reverse shell does, it basically gives you remote access to a computer, and specifically access to the shell. So whether it's a PowerShell, whether it's like a command prompt or a bin bash. But we can see we can execute this v2 runner script, and we get a shell pop on this side here, who I might Ben, hostname, whatever. So it unpacks the image. So when you execute Python script, when you execute the Python script, it takes open the image, and then it goes pixel by pixel, and it pulls out the RGB components and extracts the least significant bit from all of those one by one until we've got a big string of zeros and ones. It then finds out where there's 8 consecutive zeros to mark the end of the data, and it cuts off all the data from that point. So now we've just got our encoded message, and it's in binary format, zeros and ones. So we convert that back to plain text, and it's actually a base64 encoded string. We decode that, and then we execute the second stage payload, which contains shellcode and normal Python code to get the reverse shell, and we get a reverse shell pop on this side. So I'm going to try basically run some commands on the left-hand side to show how it reflects. I'm going to try use the touch command to create a file, and then I realise that's a Linux command, not Windows. So I'm going to think for a few seconds, saying, what else can I use? What else can I use? Maybe make directory, make dir, you have been pwned. And you can see over here, folder created, you have been pwned. So that was a quick demo. The shellcode I chose to use acts as a reverse shell. You could be creative, do what you want with it. If you use certain shellcode, it may not bypass. Just to show you can upload both scripts. The runner script and the sort of image both come out with 0 virus total hits. So enough with the sort of proof of concept. Let's get into some sort of sheets, get into the blue team side, and we'll do some analysis. I'm particularly looking at a malware delivery campaign here, and it involves a malicious Word document. The hash is there if you need it, and we can see this is sort of an image of what the Word document would look like when you open it, and we can see your typical macros have been disabled, enable content in order to get execution of the macro and do whatever the malware does. So we can use the OLE tools. These are a set of command line tools for Linux, which allow you to analyze Office documents. And we can use the OLE-ID command to get a generalized idea of what this particular document contains. So we can run OLE-ID on georates.docx. We can see, interestingly, there are no VBA macros, and there are no XLM macros. So I don't know why they were trying to enable content there, because there is no macro. What we do see is there is an external relationship, and it says use the command OLE-OBJ for details. So we'll do that. We can see it found in a relationship attached template with an external link. So I've got the IOC there. This domain, www.xmlschemeformat.com, is hosting a Word template externally. So I guess the point of this was that, if this template was in the document itself, it would easily be able to be scanned, and maybe if there was macros in it, would flag up as malicious. However, if they sort of pull it down only dynamically when the user has opened it and downloaded it, then maybe it will bypass some sort of AV. That's my guess. But what we can do, we've got this template, we can pull this down, and we can use the OLE-ID command on the template itself, and we can see it is a file format. It is a macro-enabled template, and it does contain VBA macros. The hash is there once again. We can now use the OLE VBA command, and this will extract the VBA macro from the template. So we'll do that, and we can get the VBA script here. And just by looking at this, you can tell it's malicious. It's heavily obfuscated, and I'm not going to bore you and piece it all back together. I'm just going to show you that's what it translates to. Roughly, this is what is happening upon execution. wscript.shell.run is being used to run this command, and it's actually multiple commands chained together with sort of the and symbol. So let's break these commands down. We start off by, so if the users open the Word document, they have enabled macros, enabled content. This externally hosted template pulls down and executes this code. It first of all changes the directory to local app data. It then uses the curl, which is a command line tool, which allows you to interface with the HTTP protocol or maybe download web files, whatever. And we see curl being used to download a JPEG file from this www.xmlscheme format domain once again. So that's interesting, right? There's a JPEG being downloaded. We then see certutil. So certutil is a command line tool. It's totally legitimate. Its use is for sysadmins, whatever, want to deal with certificates. They will use this command line tool. It's also abused by threat actors in the wild. They can do pretty creative stuff with it, and in this case we can see they're decoding this JPEG and it's magically turning into an exe. And we then see there's this msdll_update.exe binary which is executed. So the JPEG goes to exe and then that's executed. Let's sort of break this down. We can download this image ourselves, and we can use the file command on Linux to sort of verify, is this actually a JPEG? And it is. And then we can open it, and we can see this is a photo of the James Webb Telescope in space. So that's a bit strange, because I thought something with a certificate was going on, and we were decoding it was an exe, but this looks like a totally legitimate image, which I guess if you saw it on your file system and you didn't download it, that may raise concerns. But it doesn't stand out as being malware or malicious. However, let's dig into this file. We're going to use the strings command. This is another sort of command line utility for Linux, which if you've got a binary file which isn't plain text, you can pull out all the plain text strings from the file. And we can do that. And we can see up the top all the sort of strings you would expect to see associated with the header of a JPEG file. And then we scroll down and down, and then we've got this big bulk of text. And we can see it starts with the begin certificate. So this is what we're looking for. And then it contains lots and lots of base 64 encoded text. And then it ends with end certificate. So when I eventually scroll down, there we go. End certificate there. And it's base 64 encoded text. So we can copy that base 64 text, and we can open up CyberChef. And we'll use the from base 64 function. And we can see some recognizable strings at the top. MZ, and this program cannot be run in DOS mode. So, if you didn't know, this is a portable executable, an exe file. This is the file header You always see MZ at the top here. So yeah, it's an exe. We knew it was going to be an exe, right? Because we saw it as output to msdll update.exe. So we've got this exe. If we wanted to, we could use the function detect file type within CyberChef, and that will just confirm this is a sort of portable executable. We can upload this to VirusTotal. We can see, it's malicious. This is actually part of a campaign dubbed Go Webfuscator. It's Go compiled malware. It uses some interesting techniques for encryption and obfuscation, and C2 is over encrypted DNS. So interesting stuff. There are a few other sort of notable cases I should mention. One of them, these two, both Jai and Izzy, they both from the Huntress team, really great team. And earlier this year, a couple of months ago, they were dealing with a particular campaign, malware delivered via email, phishing, and there was a big execution chain, VBS to PowerShell, and then there was a web download of a definite wallpaper. And this definite wallpaper had an executable embedded in it. It had a Xworm loader embedded within the image. Interesting stuff. If you would like to read more into this in your own time, there is a GitHub repository here. It contains a lot of different sort of publicly reported intrusions and cases which use steganography for evasion. Really interesting stuff, and there are some really creative use of steganography in these. So I would definitely recommend checking that out. And there was one last one I thought I wanted to add, but I'm not really sure if it counts as steganography, but I think it's a pretty interesting technique. So Talos Intelligence, they released a blog post on the Azeroth malware samples, and what we've got down here is sort of the assembly and the associated with a particular Azeroth binary sample. And we can see some strings there representing YouTube channel, so a URL to a YouTube channel, and it looks like maybe different YouTube channels. So interesting stuff. What we can do, we can extract all of these sort of links, and we can see, there's a load of different about pages to the YouTube channels. So what is going on here? We can visit one of these YouTube channels and actually see the content of the about page or the description, and we can see the description contains base64 encoded data, and it's actually encrypted as well, so if you decoded that, it would look messy. Anyway, if you could decode it, they would decode to a list of domains. So if you decrypt it, the malware pulls its sort of domain list for its C2 from YouTube channel descriptions. I thought this was really cool. That's why I added it in. I believe I'm finished. Is there any questions?
With the shellcode,
yes.
Because it's like normally of a fixed size, I'm assuming you have to have an image that has a certain amount of pixels. Like, how small can the image be?
That is a very good question. I don't entirely know how small the image should be. Obviously, if you choose a big image, you've got enough space. You can encode a lot of data, just plain text data. You can encode a hell of a lot of it, even on a relatively small image. But if it's a high resolution image, you won't have any issues. You won't get close to the sort of upper limit. Yeah. Yes, Will? It's a good question. I would say look at the threat hunt related to the process activity. So if you see maybe a curl followed by some cert util, and I mean, if you see cert util, you could probably do a threat hunt based on the command line arguments of a cert util process if it contains in the command line arguments maybe a file type for JPEG, PNG. That's it's going to be dodgy. Nobody's actually, I don't think nobody actually sort of encodes secret text in images for legitimate purposes. So I would do something related to process activity. It's quite hard to hunt for, but yeah. Anyone else?
So the good EDR would capture. Is that just seeing the shellcode once it's put together in memory, or?
Yeah, I think it's a combination of that. If I expect it depends what port. I use 31337. I think there's multiple things which an EDR it should capture on. Memory is one of them. Mixed into the network traffic. That probably when you use this MS Venom generated shellcode, that I don't actually know what the detection logic for it is. I don't know whether there are certain DLLs which are loaded or what actually happens, but I'm almost sure it would get killed just because how sort of prevalent MS Venom use is. And if I dropped, say, instead of when I generated the shellcode, I choose the format to be in Python. If I generated that as an executable and I've done this and you just drop that on your Windows host, it gets killed. So yeah. Any other questions? All good. Thank you.
Brilliant.